Look at the light in your room. Now imagine Albert Einstein sitting quietly beside you, watching you press the switch. Click. The bulb turns on and the room fills with light. To your eyes, it feels instant. Your finger moves, the light appears, and there seems to be no delay at all. For most of human history, that is exactly what people believed. Light felt infinite, immediate, almost magical. But Einstein would not look at that light as something ordinary. He would ask a deeper question. Did the light arrive instantly, or was your room simply too small to notice the journey? Because light does travel. It moves through space at about 300,000 kilometers per second, fast enough that a light bulb feels instant, fast enough that common sense cannot catch it, but not infinite. And once we discovered that light has a speed, everything changed. Because if light takes time to travel, then you never see the universe as it is right now. You see the sun from about 8 minutes ago. You see distant stars from years, centuries, or even millions of years ago. You are not looking at space, you are looking at history. But Einstein took the mystery even further. He realized the speed of light is not just the speed of brightness. It is the speed limit of reality itself. It is the speed of information, the speed of cause and effect, the speed that protects the order of time. If anything could move faster than light, the future could interfere with the past. A message could arrive before it was sent. An effect could happen before its cause. So maybe light is not just fast. Maybe light is the rule that keeps the universe from breaking its own story. And this is the question Einstein forces us to face. Why does the universe have a speed limit? And why is light the thing that reaches it? To understand why light is so fast, we first have to understand how humanity discovered that light has a speed at all. Because for a long time, that idea did not feel natural. If someone throws a stone, you can see the stone move. If a bird flies across the sky, you can follow its motion. If a car passes on the road, you can watch it approach, reach you, and disappear. But light does not behave like that in everyday life. You open your eyes, and the world is already there. The walls, the sky, the trees, the face of the person in front of you. Everything appears at once. There is no visible travel time, no clear delay, no moment where the image is halfway between the object and your eyes. So for centuries, it was reasonable to believe that light might be instant. Then came the first great challenge. How do you measure something that is too fast for ordinary human experience? Galileo tried. His idea was simple and brilliant. Two people stand on distant hills with covered lanterns. The first person uncovers his lantern. As soon as the second person sees the flash, he uncovers his own lantern. The first person then tries to measure the delay between sending the light and receiving the return flash. In theory, this should reveal the travel time of light, but in practice, it failed. Not because Galileo was foolish, but because the distance was too small and human reaction time was too slow. The delay caused by light traveling between the hills was far smaller than the delay caused by the people moving their hands. So Galileo could not measure the speed of light. But his failure was important. He did not prove that light was infinite. He showed that if light had a speed, it was far faster than anything his experiment could catch. The laboratory was too small. To measure light, humanity needed a bigger stage. Not a hill, not a room, the solar system. This is where the story becomes beautiful. In the 1600s, the Danish astronomer Ole Rømer was observing Jupiter's moon Io. Io moves around Jupiter in a very regular pattern. It disappears behind Jupiter, then comes back out again, like a cosmic clock ticking in space. If Io's orbit is regular, then astronomers should be able to predict exactly when it will disappear and reappear. But Rømer noticed something strange. When Earth was closer to Jupiter, Io's eclipses seemed to happen on time. But when Earth moved farther away on the opposite side of its orbit around the Sun, the eclipses appeared late. The moon itself was not changing its schedule. Jupiter was not suddenly confused. The problem was the message. The light carrying the image of Io had farther to travel when Earth was farther away. So the event happened, but the news of the event arrived late. That was the breakthrough. Light was not instant. Light was a messenger, and a messenger needs time to cross distance. This changed the way we see the universe. When you look at the sun, you do not see the sun as it is this exact second. You see it as it was about 8 minutes ago, because sunlight takes about 8 minutes to reach Earth. If the sun changed suddenly, we would not know immediately. The information would need time to arrive. When you look at Jupiter, you see it as it was many minutes ago. When you look at the stars, you may be seeing light that began its journey years, centuries, or even thousands of years before you were born. So the night sky is not a live broadcast. It is a delayed message from the past. This is the first major idea that prepares us for Einstein. The universe does not give us instant access to reality. It gives us signals, and every signal has a travel time. But discovering that light has a speed raised a deeper question. What is light? Is it made of tiny particles flying through space like bullets? Or is it a wave spreading outward like ripples on water? For a long time, this was one of the biggest battles in physics. Newton believed light behaved like particles. Later experiments showed light could also act like a wave. The famous double-slit experiment revealed that light could interfere with itself. It could create bright and dark patterns like overlapping ripples. That seemed to prove light was a wave. But then came another problem. A wave of what? Sound is a wave in air. Ocean waves are waves in water. A rope wave travels through rope. So if light is a wave traveling through space, what is waving? Scientists once imagined that space must be filled with an invisible substance called the ether. This ether was supposed to be everywhere, between planets, between stars, even passing through your body. It was invented because people believed a wave must always need a medium. But the ether created strange problems. It had to be stiff enough to carry light incredibly fast, but thin enough that planets could move through it without slowing down. It had to be everywhere, but impossible to detect. Then James Clerk Maxwell changed the story. Maxwell studied electricity and magnetism. Before him, they looked like separate forces. Electricity was sparks, batteries, lightning. Magnetism was compasses, iron, and invisible pulling forces. But experiments showed they were connected. A moving electric charge could create a magnetic effect. A changing magnetic field could create an electric effect. Maxwell wrote equations describing this relationship, and those equations revealed something astonishing. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field, and together they can sustain each other as a wave moving through space. Electricity creates magnetism. Magnetism creates electricity. The wave carries itself forward. Then Maxwell calculated how fast this electromagnetic wave should move, and the number that came out was the speed of light. That was the revelation. Light is not just brightness. Light is an electromagnetic wave. The colors you see, the warmth of the sun, the glow of a lamp, the beam from a star, all of it is electricity and magnetism dancing together through space. But now physics faced a strange crisis. If light is a wave and its speed is fixed by Maxwell's equations, then fixed relative to what? Imagine you are on a moving train and you throw a ball forward. To you, the ball moves at one speed. To someone standing on the ground, the train's speed adds to the ball's speed. That is normal. Speeds add. But light refused to behave normally. Physicists expected that if Earth was moving through the ether, then light should appear to move slightly faster in one direction and slightly slower in another. So the Michelson-Morley experiment was designed to detect this difference. It found nothing. No ether wind, no change in light speed. No matter how Earth moved, the measured speed of light stayed the same. This was not a small problem. It was a crack in the foundation of common sense. If you chase a beam of light, shouldn't it move away from you more slowly? If you move toward it, Shouldn't it approach faster? Everyday logic says yes, but nature said no. The speed of light is the same for every observer. This is where Einstein enters the story. Einstein looked at the problem and did something radical. He did not try to save the ether. He did not assume the experiments were wrong. He took the speed of light seriously. He asked, what if the speed of light is not changing? Because space and time are the things that change. That single thought changed physics forever. Speed is distance divided by time. So if the speed of light must remain constant, then distance and time cannot be absolute. They must adjust depending on motion. Moving clocks tick differently. Moving rulers measure differently. Time can stretch. Space can shrink, not as an illusion, as reality. This is special relativity. And this is why Einstein's connection to light is so important. He did not simply ask how fast light moves. He asked what the speed of light reveals about time itself. The answer was shocking. Time is not the same for everyone. There is no single universal clock ticking above the universe. There is no perfect now shared by every star, planet, and person. The speed of light forces each observer to have their own measurement of time and space. And yet, through all of this, one thing remains constant: light. That is why light is not just fast. Light is the measuring rod of the universe. It is the rule that tells space and time how to bend around motion. It is the reason the universe cannot be understood with ordinary common sense alone. And once Einstein accepted that, the next mystery became even deeper. Why can light reach this cosmic speed limit, while everything with mass can only chase it forever? Einstein's answer begins with one simple difference. Light has no rest mass. A photon does not need an engine. It does not start slowly and then accelerate like a car. It does not begin at zero and build up speed like a rocket leaving Earth. The moment a photon exists, it is already moving at light speed. That is its natural state. But anything with mass has a very different fate. You, me, a stone, a planet, a spaceship, even a tiny proton inside a particle accelerator. All of these have mass, and mass means resistance to acceleration. The faster you push an object, the harder it becomes to push it even faster. This is not just a weakness in our technology. It is not because our rockets are too small or our engines are not advanced enough. It is built into reality. In Einstein's universe, energy and mass are connected. The famous equation E equals mc squared tells us that mass and energy are two forms of the same thing. When you add energy to a massive object to make it move faster, you do not simply get more speed. Near the speed of light, more and more of that energy goes into increasing the object's resistance to further acceleration. So the object gets closer and closer and closer, but it never reaches light speed. Particle accelerators prove this every day. Scientists can push particles to 99% of the speed of light, then 99.9%, then 99.999%. But no matter how much energy they add, particles with mass never cross the final line. The speed of light is not a finish line matter can touch. It is a horizon. You can approach it forever, but you cannot arrive. To actually push a massive object to light speed would require infinite energy. And infinite energy is not something the universe gives out. But photons are different. They do not carry rest mass, so they are not trapped in the same way. They move at the maximum speed because there is nothing inside them that needs to be dragged up to speed. This is why light seems almost supernatural. But Einstein's deeper lesson is that the speed of light is not really about light alone. Light is simply the most visible messenger of a deeper law. Gravity travels at this limit. Electromagnetic information travels at this limit. Cause and effect are protected by this limit. If the sun could magically vanish, Earth would not instantly know. For about 8 minutes, Earth would continue moving as if the sun were still there, because even gravity's change would need time to reach us. That is how serious this speed limit is. It is not just the speed of brightness, it is the speed of information, and this protects the order of events. Imagine if a signal could move faster than light. In some frames of reference, that signal could appear to arrive before it was sent. A warning could reach the past. An effect could appear before its cause. The story of reality would become confused. Einstein's universe does not allow that. The speed of light keeps the timeline from collapsing into contradiction. It keeps the universe from becoming a place where answers arrive before questions and consequences happen before choices. This is why many physicists say the speed of light should really be called the speed of causality. It is the fastest speed at which the universe can update itself. Now, this creates one of the strangest ideas in all of science. From our point of view, light takes time to travel. Sunlight takes about 8 minutes to reach Earth. Light from nearby stars takes years. Light from distant galaxies can take millions or billions of years. But from the mathematical point of view of a photon, time does not pass in the normal way. Einstein showed that the faster something moves, the slower its time runs, compared with a slower observer. If an astronaut travels close to light speed, less time passes for that astronaut than for people back on Earth. Push that idea to the limit. At light speed, time reaches zero. A photon leaving a distant star may travel for millions of years from our perspective. But for the photon itself, there is no experience journey in the ordinary sense. Emission and absorption are connected without the photon waiting through time the way we do. This is difficult to imagine because we are creatures of mass. We live below the limit. We age. We wait. We move through time moment by moment. Light lives on the edge. And because light lives on the edge, it reveals the shape of space-time itself. Einstein helped us understand that space and time are not separate things. They are woven together. You are not only moving through space, you are also moving through time. Even sitting still, you are moving through time. You are aging. You are traveling into the future. But when an object moves faster through space, it moves differently through time. Motion through space and motion through time are connected. This is why a fast-moving clock ticks differently from a clock at rest. Light is the extreme case. It uses the full cosmic limit for motion through space, so there is no normal passage of time left for it. This is one reason the speed of light feels so mysterious. It is not just a number. It is a relationship between space and time. In fact, calling it the speed of light can be misleading. It makes it sound like the number belongs to light only, but the constant belongs to space-time. Light simply reveals it. It is like measuring the exchange rate between space and time. The universe has a built-in conversion. 1 second of time corresponds to about 300,000 kilometers of light travel in space. That number is not random decoration. It is part of the architecture of reality. Now let's bring this down to something you can see. Light always travels at light speed in a vacuum, but inside materials like water, glass, or diamond, light appears to slow down. This is why lenses bend light. This is why eyeglasses work. This is why a straw in a glass of water looks bent. But what does slow down really mean? A photon moving between atoms still travels at light speed, but inside a material, light interacts with the atoms. The electromagnetic wave disturbs electrons. The electrons respond, and the wave continues. These interactions create delays, so the overall progress of light through the material becomes slower. Think of it like a very fast runner crossing a crowded room. When there is open space, the runner moves at full speed. But if the runner must stop again and again to pass through a crowd, the total trip takes longer. The runner did not become weak. The path became interactive. In dense materials, the delay is greater. That is why light moves more slowly through diamond than through air. And this leads to a strange effect. In a vacuum, nothing with mass can outrun light. But inside water, light's effective speed is lower. A high-energy particle can move through water faster than light moves through that water, though still slower than light in a vacuum. When this happens, the particle creates a kind of light shock wave called Cherenkov radiation. It often appears as a blue glow in nuclear reactor pools. It is not breaking Einstein's universal speed limit. It is only outrunning light inside that material. The true cosmic limit remains safe. Now let's look at sunlight. When sunlight touches your face, you may think that light was created 8 minutes ago at the surface of the sun. But the deeper story is older. The energy that becomes sunlight begins in the core of the sun, where nuclear fusion converts hydrogen into helium. Photons are produced deep inside an extremely dense environment. But the sun's interior is so crowded that a photon cannot simply fly straight out. It is absorbed, re-emitted, scattered, redirected again and again. A journey that would take seconds in a straight line can take thousands or even hundreds of thousands of years because the photon's energy bounces through the solar interior in a chaotic path. Then finally, after an incredibly long escape, that energy reaches the surface. From there, it crosses space to Earth in about 8 minutes. And then it ends its journey in your eye, on your skin, on a leaf, on the surface of the ocean. So the light you see is not simple. It is an ancient traveler. It carries a history. And the same is true on the largest scale of all. For the first hundreds of thousands of years after the Big Bang, the universe was not transparent. It was hot, dense, and filled with charged particles. Light could not travel freely because it kept scattering again and again. The universe was like a glowing fog. Then, as space expanded and cooled, electrons and protons joined to form neutral atoms. Suddenly, light could move freely. The fog cleared. That ancient light is still around us today. It is stretched with the expansion of the universe into microwaves. We call it the cosmic microwave background. It is the afterglow of the early universe, a fossil made of light. When scientists study it, they are not just looking far away. They are looking back toward the childhood of the cosmos. This is one of the greatest consequences of light having a finite speed. Astronomy becomes time travel. Not science fiction time travel, where we step into a machine and visit the past. Real time travel through observation. Every telescope is a time machine. The farther it sees, the older the light it receives. And because light has a limit, the universe has a visible horizon. There are regions so far away, and space is expanding in such a way that their light may never reach us. They exist, but they are beyond our cosmic communication. The universe is not only big, parts of it are permanently unreachable. This makes our moment in cosmic history precious. We live at a time when ancient light can still reach us. We can still detect the afterglow of the early universe. We can still see galaxies far beyond our own. We can still read the story written in radiation, color, and motion. And speaking of color, light also explains the beauty of the everyday world. The sky is blue because molecules in the atmosphere scatter shorter wavelengths of sunlight more strongly than longer wavelengths. Blue light gets scattered in many directions, so wherever you look in the daytime sky, blue light reaches your eyes. At sunset, sunlight travels through a much thicker layer of atmosphere. Much of the blue light has been scattered away before the sunlight reaches you directly. What remains is richer in red, orange, and gold. The sunset is not painted by emotion. It is painted by scattering. Leaves look green because chlorophyll absorbs certain wavelengths of light more strongly, especially red and blue, while reflecting more green light back to our eyes. Color is not simply inside objects. Color is a conversation between light, matter, and the biology of your eye. And our eyes see only a tiny part of the full electromagnetic spectrum. There are radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays all around the universe. Human vision catches only a narrow slice. The night sky looks dark to us because our eyes are limited. In radio waves, X-rays, and microwaves, the universe is glowing with activity. Science extends our vision. Radio telescopes, space telescopes, infrared cameras, and X-ray observatories allow us to see the parts of light our bodies cannot detect. Every time we open a new window in the spectrum, the universe becomes larger, stranger, and more alive. And finally, light changes our idea of now. Before Einstein, it was natural to imagine one universal present moment, a single cosmic clock ticking everywhere at once. But relativity breaks that picture. If light speed is the same for every observer, then different observers moving differently can disagree about whether two distant events happened at the same time. This is not a mistake. It is not an illusion. It is how space-time works. There is no universal now spread across the entire cosmos. There are only perspectives. This may be the most uncomfortable lesson Einstein gave us. Time is not the rigid river we imagined. It bends with motion. It stretches with speed. It is woven into space. And light is the thread that reveals the pattern. So why is light so fast? Because light has no rest mass. Because it moves at the maximum speed allowed by space-time. Because it carries information, energy, and the visible history of the universe. Because its speed protects causality. Because without that limit, time itself would lose order. But there is another way to say it. Light is fast because the universe needs a messenger. A messenger fast enough to connect stars and planets. A messenger steady enough to define space and time. A messenger limited enough to preserve cause and effect. And we, slow creatures made of atoms, get to receive that message. Every sunrise, every shadow, every reflection, every star in the night sky, every color your eyes have ever seen is light telling you a story, so the next time you flip a switch, do not treat that glow as ordinary. Think of Galileo trying to catch light between two hills. Think of Reaumur watching Jupiter's moon arrive late. Think of Maxwell discovering electricity and magnetism moving together. Think of Einstein realizing that light's constant speed means time itself must bend. And think of the photon, born in a star, traveling across space, carrying the past into your present. Light is not just what lets you see the universe. Light is how the universe speaks. And maybe that is why Einstein never treated light as a simple thing. Because hidden inside its speed is the secret of time, space, causality, and reality itself. If this explanation made you see light differently, subscribe to the channel, because here we explore the universe through Einstein's deepest ideas. And before you go, comment below. What feels more mysterious to you? That light is so fast, or that time changes to keep its speed constant?